Hi, this is a video that's meant to serve as an introduction to rational functions. We've seen that given polynomials, we can add, subtract, multiply, and divide them. An interesting fact is that whenever you add two polynomials, then the resulting equation is also a polynomial. The same is true when you subtract or multiply. Anytime you use these operations with two functions, the function that you get is also a polynomial. This is not true, however, when we use division. If we take a polynomial and divide it by another polynomial, we get what's called a rational function. So a rational function is anything of the form p of x over q of x, where p and q are both polynomials. So here are some examples. In the first polynomial f of x, we have a degree 2 polynomial divided by a degree 3 polynomial. You can see a graph of this in the upper right-hand corner. G of x is a degree 1 polynomial divided by a degree 2 polynomial, and the graph of that is in the middle. And h of x is a constant, or degree 0, divided by a degree 1 polynomial. Now, as you can see, these rational functions can be very interesting in how the graphs look. The goal of this video is to figure out what these graphs will look like based on analysis of these functions. So we're going to start with the basic rational function, f of x is equal to 1 over x. Anytime you have a function and you need to graph it, and you don't know what it looks like in the least, what you want to do is simply plot points. So if we were to plot the points 1, 2, 3, 4, and 10, and then the negatives of those, we would see the points follow this pattern like so. Now, an interesting thing happens here when we try to plug in 0. If we evaluate f of 0, then we get 1 divided by 0, which is undefined. What that means is that point just won't be on the graph. So here we can get a little bit of an indication of what this function is going to look like. It looks like it's going to sort of get closer and closer to the x-axis as it gets further and further away from the y-axis. But what happens as it gets close to the y-axis? Well, let's plot some more points. If we plot the points 1/2, 1/3, 1/4, etc., we see that the function gets higher and higher the closer we get to the y-axis. On the left-hand side, the function will get lower and lower the closer we get to the y-axis from the left. The interesting thing here is that the closer you get, the higher the function becomes. And so this function actually reaches up, 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 all the way to infinity. Now, connecting the dots, we get a look at what this basic rational function looks like. So one thing to point out is that we have something new that we haven't seen before with our polynomial functions, and that is what we call an asymptote. An asymptote is a line that the graph approaches but never reaches. In this case, we have two types of asymptotes. The first one is a vertical asymptote. We saw that as the function got closer to 0, it got very high or very low depending on which side it is. In this case, we say that the vertical asymptote is equal to x equals 0. That's the equation of this vertical line. This function also has a horizontal asymptote. Notice that as the function gets further and further from the y-axis, it gets closer and closer to 0. In this case, we would say that the vertical or the horizontal asymptote is y is equal to 0. That is, the equation of the line y equals 0 is this horizontal line that the function approaches. So we will be looking at asymptotes for different rational functions. So first, let's talk about graphing these by transformations. Here we see that we have the basic function 1 over x, and there's been a couple of transformations done to it. The -1, or the negative in front, makes it a reflection across the x-axis, and adding 5 to the end means that we're going to shift it up by 5. So in order to graph this, we start with our basic function, 1 over x. We reflect it first, and then we shift it up. This would be the graph of f of x is equal to negative 1 over x plus 5. In this case, notice that there is a vertical asymptote at x equals 0, and the horizontal asymptote is at y equals 5. It has shifted up with the graph. Another example of graphing by transformations, here we have g of x is equal to 1 over x plus 4 minus 3. In this case, the transformations that we have is the x plus 4 on the bottom is going to be a shift to the left by 4, and the minus 3 is going to be a shift down by 3. And so in order to graph this, we would once again take the original 1 over x, then we would shift it to the left by 4 and shift it down by 3. So this would be g of x is 1 over x plus 4 minus 3. Here we have the vertical asymptote of x equals negative 4 and the horizontal asymptote of y equals negative 3. We also may want to talk about the domain and the range. In this case, notice that when you have the vertical asymptote at negative 4, at that point, the graph does not have an x value there. That is, there is no point if you tried to plug in negative 4 into the function. Notice if you did try to plug in negative 4, you would get 1 over 0 minus 3, which of course is undefined. So we need to throw that point negative 4 out. The way we denote this, of course, is just negative infinity to negative 4, but with a parenthesis saying we're not going to include it, union negative 4 to infinity. The range can be found in much the same way. If we wanted to find the x and the y intercepts of this, we can see that on the graph, you can tell that the x-intercept is going to be somewhere between, it looks like negative 3 and 4, and the y-intercept is going to be somewhere between maybe 2 and 3. The process for finding these is the same as it's been before. In order to find the x-intercept, what you do is you plug in 0 for your y value and then solve for x. So in this case, we replace g of x with 0, and then we solve the resulting equation. So 0 is equal to 1 over x plus 4 minus 3. If you were to solve that, you get x is equal to negative 11 thirds. In order to find the y-intercept, we plug in 0 for x. When you do that and solve, you get that y is equal to negative 11 fourths. Now we want to look at graphing these rational functions that can't be done through transformations. In this case, we have this rational function 2x plus 7 over x minus 3. Just like when we studied polynomials, what we're going to do is analyze this function by looking at different aspects of it. We're going to follow a several-step process, and each step will tell us something about the function. The first step is that we need to write the function in factored form. That is, if we have something that is not factored, we need to factor it. In this case, it's already factored, so step 1 is already done. Step 2 is we want to plot the zeros, the vertical asymptotes, and the y-intercept. So let's talk about each of these in turn. In order to find the zeros, or the x-intercepts, we have to look at where p of x is equal to 0. That is, where the top polynomial is equal to 0. So just taking 2x minus 7 and setting it equal to 0 and solving gives us that the x-intercept will happen at negative 3.5. In order to find the vertical asymptote, we do the same thing except for with the bottom of the function. That is, we take the denominator and set it equal to 0 and solve. In this case, x minus 3 is equal to 0. Solving that, we get that there's a vertical asymptote at x equals 3. And finally, to find the y-intercept, you simply evaluate f of 0. That is, you plug in 0 for x. When you do that, the x's basically go away, and you're left with 7 over negative 3, which is around negative 2.33. So let's graph these things that we found. We saw that there was a y-intercept at negative 2.33 or so. We saw that there was an x-intercept at negative 3.5, and we found that there was a vertical asymptote at 3. The way that we should denote this vertical asymptote is a dotted line that's straight up and down through 3. So this is the end of step 2. This is as much as we can plot from this information. The next thing we want to look at is the horizontal asymptotes. Now, some rational functions don't have horizontal asymptotes, and so we're going to look at how to find them if they are actually there. So they're going to follow these rules. There's 3 possibilities when it comes to the end behavior of a rational function, or the horizontal asymptotes. The first case is if the degree of the polynomial on top in the numerator is less than the degree of the denominator, then there's a horizontal asymptote of y equals 0. In other words, if the power, the highest power on the bottom, is bigger than the highest power on the top, then the horizontal asymptote is y equals 0, which means that the graph will approach the x-axis as it gets further and further from the middle. The second case is when the degrees of the numerator and the denominator are equal. In this case, there will also be a horizontal asymptote, but that horizontal asymptote will be equal to y equals an over bm, where an and bm are these leading coefficients. So if the highest power on the top is equal to the highest power on the bottom, then we look at the coefficients of those 2 terms, and that determines the horizontal asymptote. And finally, if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. And in this case, the function, this rational function, will go off to infinity or negative infinity, much like the polynomials did. So in this case, looking at the degree of the top and the bottom, we see that the highest power on the top is 1, and the highest power on the bottom is also 1, so they have the same degree. And so therefore, we have to look at the coefficients of those 2 terms. In this case, the coefficient of the top term is 2, the coefficient of the bottom term is 1, so that tells us that there's going to be a horizontal asymptote at 2 over 1, or simply y equals 2. So we can draw that horizontal asymptote as a horizontal line that goes through 2. In this case, I also like to use a dotted line to indicate that there is a horizontal asymptote here. The next step is to determine where this function is positive and where this function is negative. So here is a fact. A rational function can only change signs, that is, it can only go from positive to negative or from negative to positive, either at a 0, where it crosses the x-axis, or at a vertical asymptote. So what we do is we partition the number line with these things, that is, with all the zeros and with all the vertical asymptotes. In this case, it would look something like this. We had a 0 at negative 3.5, and so we partition the number line there, and a 0 at positive, or a vertical asymptote at positive 3. So we partition it there. Now we need to plug in a point into the original function from each of these regions. We have these 3 regions that have been created, the one that's less than 3.5, the one that's sort of in the middle, and the one that's greater than 3.5. Plugging a value in for each of those regions, we see that the first region is positive, the second region is negative, and the third region is positive. We're using the fact here that a rational function can only change signs when it crosses either a zero or a vertical asymptote. What that means is if you plug in one value that's less than 3.5, say you plugged in -10, if that number that you get when you plug that in to the function is positive, that means that all the numbers less than 3.5 will be positive. The same thing for the middle region. Plugging in one number and finding that it's negative means that all the numbers in that region between -3.5 and +3 are also negative. I like to think of these test points as representatives. So they perfectly represent which side of the x-axis something is on, that is, whether the numbers are positive or negative. Now, using this sign chart, we can make a rough sketch of this rational function. What we know is that if a region is negative next to a vertical asymptote, it has to approach the vertical asymptote by going down to -infinity. And if it's positive in that region, it has to approach the vertical asymptote by going positive. Also, the graphs must approach the horizontal asymptote as they go out away from the middle. So in this case, we could say that the graph is going to look something like this. Notice that where the regions here are positive, the graph is above the x-axis, and where the region is negative, the graph is below the x-axis. And this would be a rough sketch of this rational function. Let's look at another example. In this case, we have the function f of x is equal to x plus 1 over x squared minus x minus 12. Once again, we can't use transformations of our original 1 over x graph, so we have to analyze this graph and pick out those pieces of information that we can tell from this. So step 1 is we need to write this in factored form. Here, since the bottom can be factored, we can write this as x squared minus x minus 12 as x plus 3 times x minus 4. This is an important step in the coming steps. Step 2, we want to find the zeros, the vertical asymptotes, and the y-intercept. In this case, remember, we find the zeros by setting the numerator equal to 0 and solving. So we have an x-intercept, or a 0, at -1. The vertical asymptotes are found by taking the denominator and setting it equal to 0. So here we see that we're going to have two vertical asymptotes. One is going to happen at -3, and the other is going to happen at +4. And finally, the y-intercept is here at -1 over 12. If we were to graph this information, we would see that here is our y-intercept that's just under 0 at -1/12. Here is the x-intercept at -1. And we have our vertical asymptotes at -3 and +4. Now we need to find the horizontal asymptote. In this case, the degree of the numerator is 1 and the degree of the denominator is 2. Since the degree of the denominator is bigger than the degree of the numerator, we see that there is a horizontal asymptote of y equals 0. That means that the horizontal asymptote will be the x-axis. And this is where the graph will approach as it gets towards infinity and -infinity. Now we have to make our sign chart. Remember, we're going to partition this with all the zeros and the vertical asymptotes. And so those numbers are going to be -3, -1, and 4. These are the points where this function can change from positive to negative. By plugging in test points in each of these 4 regions, we see that this function is negative anywhere less than -3. It's positive in between -3 and -1, and negative in between -1 and 4, and positive, once again, greater than 4. Remember, we can get these by simply plugging in any point from that region into the original function. Finally, we look at this sign chart and the information that we have, and we sketch a rough sketch of what this graph might look like. So we know that the function is going to approach the vertical asymptotes, whether they be positive or negative, in those directions. So if it's a positive region, it's going to go to infinity as it goes up to that vertical asymptote. If it's a negative region, it's going to go down to negative infinity as it approaches that vertical asymptote. So in this case, the function would look something like this. Taking away the other things, it looks like this. So a very interesting looking function. I hope this video can serve as a good introduction into analyzing rational functions. Thanks for watching.